Hi everyone, nice to meet you all, like via remote. I'm SooHyuk and I'm currently a rising sophomore at UC Berkeley. I'm studying computer science and physics as a double major. And my interest is pursuing a research after like graduating to grad school. And I'm considering to take a research on the field of the cryptography, security, or the machine learning, which is like mostly related to computer science field. And as the one who is passionate about the computer security and the cryptography, today I'd like to present like a new field of the math topics called modular arithmetic. So maybe some of you guys have heard of like this term modular, or and like maybe some other of you guys haven't. But modular arithmetic hasn't been like taught like in the regular curriculum, because usually the math you guys have built with the official curriculum in the school is always dealing with the continuous field, which means it's not like one, and there are like always like the infinitely many real numbers between number 1 and 2, number 2 and 3, so forth. So modular arithmetic is a little bit different. So today we're going to talk about the basics of the modular arithmetic and how it can be applied to the cryptography and the secret sharing through the RSA algorithm. So today we're going to talk about the basics of modular arithmetic first. And if you guys have any kind of question or like confusions like regarding following the calculation, feel free to drop any chat or like raise your hand. I'll try to like check chat regularly. So yeah, please do so. All right, so let's talk about the basics. I mean, even like those of you guys who haven't heard of the term modular, I'm sure that you guys have been like solved or like tried some kind of math problems that use like modular arithmetic, but it's not like often officially like mentioned as a modular arithmetic in the term. So modular itself is pretty useful in some kind of setting where we need to like limit the numbers to the like predefined range. And we often define this predefined range as a number of integers, which is 0 to n-1 inclusive, and wraps around whenever you try to leave this range. So like the pretty like traditional examples are the hand of a clock. So if you'd like to say, if you're asked what time it will be 13 hours from 1 p.m., you say just it's 2 a.m. rather than 14. So since our clock only displays like from 0 to 12, and we assume that our clock displays 12 as 0, we are just limiting numbers to a predefined range from 0 to 11 inclusive. So whenever you add two numbers in this setting, you just divide them by 12 and provide the remainder as the answer. Another example is the days of the week. So if we just assume that we call the 0th day as Sunday, first day is Monday, day 2 is Tuesday, and blah, 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 and day 6 is the Saturday, so forth. Then it is also equivalent to the addition of the integer multiples, because if today is Thursday and someone asks you, why is that day like after 5 days from today? We just say it's day 2, which is Tuesday, instead of saying day 9. So this is kind of like basics of the modular arithmetic. And we often use like this kind of symbol, x parenthesis mod m, and we read like this kind of mathematical expression as x modular m. So this just is equivalent to the value of the remainder when you divide x by m. So if you have like these 3 horizontal bars in the middle, we just read this x modular m is congruent to the r, where x is equal to some kind of integer multiples m plus r, which means, well, x modular m is equal to its remainders when we divide it by x. So for example, 29 modular 12 is 5, because 29 is basically equal to 12 times 2 plus 5. So if you divide it by 12, the remainder is equal to the 5. Same holds for the 13 mod 5. It is congruent to 3, because 13 is equal to 5 times 2 plus 3. So the remainder, when you divide 13 by 5, is 3. And another thing you need to think about is congruences. So if you have this kind of expression where x congruent to y modular m, the meaning of it can be interpreted in 3 different ways. There are just like kind of different ways to interpret this, but they are basically have same meaning. So it can be interpreted as x and y have the same remainder with respect to the modular m, or you can just think of it as x is equal to y plus km, which is some kind of integer multiples of m for some integer k. Also, you can think of it as a difference of x and y is divisible by m, because if you like move around like the equation on the second line, you get x minus y is equal to km, which means x minus y itself is a integer multiple of k. So this set -6, 1, 8, 15. This set of integers is basically congruent to one respect to the modulo 7. So you can think of it as, while we are dealing with the modular in this case, we deal all of this -6, 1, 8, 15, and so forth as the same number. Also, for -1, 1, 3, 5, this set of integers are congruent to 1 respect to modular 2. So in the mod 2 system, you can assume that all of the odd numbers are considered as a same number. So now we just talked about what kind of basic expressions and what kind of motivation we had when we use the modular arithmetic. So let's just talk about some of the properties. Our modular arithmetic also has its basis on the general arithmetic. So most of the arithmetic properties also holds for the modular. So let's talk about the addition and subtraction first. So if we wish to calculate x plus y respect to modular m, we will first add x plus y and then calculate the remainder when we divide the result by m, right? For example, if we have x equal to 14, let me just write it down. And if you have y is equal to 25, what you can do is, if you are trying to take the mod over the 12, you can think of this as x plus y is equal to 39, so which is equivalent to 3 on the mod 12. But if you have like pretty big x and y and try to find their sum or subtraction, you might need to go through some kind of tedious calculation. So what you're gonna do is, you can basically trying to distribute the mod over the subtraction, addition, and the multiplication. And I'll give you a simple proof on it. So you can think of this as a by definition of congruences we just talked about. A and B differ by some multiples of A. I mean the integer multiple. So you can think of the difference of B and A as an integer multiple of M for some kind of integer K. So here Z stands for some kind of integer sets. Similarly, the same holds for D minus C, so that like D minus C is an integer multiple in this case. So by adding these two equations together, you can like get B plus D minus A plus C equals some kind of integer multiples of M. So by the definition of congruence modular M we just talked about, we can just say this is basically same as A plus C is congruent to the B plus D over modular M, since A plus C and B plus C differ by an integer multiple, right? And the same proof can hold for the subtraction if you just change the sign. Now we're going to talk about the multiplication. So multiplication is a bit tougher if you try to like calculate it via a very traditional way of mathematics. So if you like to take, again, x equals 14, and the y is equal to 25, the value of the xy gets way larger than like when we did the summation or the subtraction. It gets 350. Of course, now you can just calculate the remainder here when you divide it by 12, which gives us 2. So you can just say So you can just say is congruent to 2 over mod 12. But like if you have like more like a way larger number, such as a 3-digit, 4-digit, or maybe some kind of 500 bits of number, it might be pretty tedious to go through this calculation. So modular arithmetic, thankfully, also holds for the multiplication as its arithmetic properties. So it's a pretty similar proof. So by the definition, it's pretty same setting. So B minus A is also integer multiples of M. D minus C is also an integer multiples of M. So if you just rearrange the equation, you can get B is equal to Km plus A and D equals Jm plus C by moving this A and C to the right-hand side of the equation. And if you multiply this B and D and expand them, you can find that it's equal to some kind of expression to the M. You can assume that KJM plus AJ plus CK, which is the number in front of M, is basically an integer because every single K, J, M, A, and C are defined as an integer. So this implies that AC and BD are congruent over mod M. So you can do the multiplication by distributing mod M over each AC and B and D. So let me give you a quick example. I'd like to give you guys about 2 to 3 minutes to try both expressions. So first example asks you a pretty traditional modular arithmetic question, such as calculate 90 to the 137 in arithmetic of modular 13. And the second one is more of the application. Modular is pretty strong when you need to find the sum of the last digits of the very big part of numbers. So what are the tens and units digits of the 7 to the 1942? And this is also a official AMC problem from the art of problem solving. So I'd like to give you guys about 3 minutes. So please try it on your own. And if you get the answer, feel free to speak out or type it in the chat. All right, cool. There are already like people who are getting the answers. Yup, 65 and 153, 154. Yeah, you guys got it correct. And if anybody has an answer or guess for the example too, feel free to speak out or send me via private or like public chat if you want. All right, cool. Seems like everybody is doing pretty well. Well, it seems like I got a lot of answers about the example 1, and a lot of students told me the answer is 12, and you guys got it correct. So how can you like actually solve it without actually calculating this big power number of 90 to the 137? So what you do is you can think of 90 as an integer multiple. Oh, what happened? 90 as an integer multiple of 13 times 7, right? And minus 1. So you can express any kind of number as integer multiples plus some kind of remainder. Or you can do 16, you can do the 13 times 6, and you can do plus 12. Anyway, like both expression holds because minus 1 and 12 are basically congruent over mod n. So what you can do is, now you can think 90 is basically congruent to minus 1 over mod 13. And now it's way easier to actually calculate this, right? Because the odd power of the minus 1 is always equal to minus 1. So now you can think like 90 to the 137 is congruent to minus 1 or 12, as like many of you guys told me. Yeah, you guys correct. Does anybody have, oh, okay, seems like someone told me, okay, the tens is 4 and unit is 9. Yeah, you got it correct. Perfect. Yeah, great job. So let me quickly talk about this one. This one is kind of pretty similar, but unlike the first one, you need to go through a bit of like pattern matching to actually solve this problem. So what you do is you basically begin by writing some of the very first powers of 7. For example, 7 is equivalent to 7 over mod 100. 7 squared is 49, which is 49 over mod 100. 7 cubed is 343. So it's congruent to the 43 over modulo 100. And 7 to the 4th is basically 2401, which is congruent to the 1. And if you like just keep watching out the last 2 digits, you can find a pattern that it repeats 7, 49, 43, 1 for every single 4 sets of the power of the 7. So now we found the pattern, and now we're gonna focus on the easiest possible digits we can actually use to the power. So we know that 7 to the 4th is congruent to 1 over mod 100. So we're gonna try to factorize 942 with the multiples of 4 and some kind of remainders. So 1942 is basically equal to 4 times 485 times 2 and plus 2. You can factorize this equation to these different powers of 7. And this first power is basically 7 to the power of 4. So you already know that it's congruent to 1 over mod 100. So the answer is just 7 squared, which is 49 over mod 100. Yeah, thanks everyone. Yeah, great job, and thanks for your participation. Now we just talked about the addition, multiplication, and the subtraction, but we haven't like dealt with the division. And it's because you need to a little bit more careful when you actually deal with the divisions. So before we deal with the divisions, there is like one thing that you guys should be aware of. which is called an inverse function. So we have already delegated the inverse function in the arithmetic way. So when you do the multiplication, if you'd like to divide it, on the other hand, if you multiply x, you divide it by x means you just multiplying it by 1 over x. Here, 1 over x is basically an inverse function of x, right? So we define inverse function to be a function that is invertible if there exists a function g such that g goes from y to x, which is in the reverse way with the property where fx should be equal to y. Then if you put that value of y in g, they recovers the x that we used in the f. So the conditions for the inverse function to exist, there are basically two conditions. And we call like this inverse function as a bijection. It's just another name of being invertible. So the first one should be the onto, which is often called the surjective. So every like y value of the function should has a pre-image of a. So for example, if you have two sets and so for example, if you have like two sets and there is some kind of error such as 1, 2, 3, and here is also 4, 5, 6. And every single 1, 2, 3 get matched before on the y sets. Then when you are trying to recover the x value from 5, you cannot find it, right? Because there was no value that gets matched with the x originally. So that's what x should be onto. Every y value that gets matched with x should have a certain preimage of x. Another one you need to think about is one-to-one. So one-to-one basically means for all a prime, if like the element called a prime in the subset A, if fa is equal to fa prime. So if there are two values that has the same function value, then those two values must be equal. So it's because, let's say, if you have like x here, and if you have a y here, if you are trying to match every single 1, 2, 3 to the 4 as we did, now you are trying to recover what was the preimage of 4 by using an inverse function. There is a problem, right? When you try to recover, to be a function, you should have a certain one y value that corresponds to 4. But here, you don't know which one do you need to recover out of 3. Is it 1? Is it 2? Is it 3? So that's why to have an inverse function, the function should satisfy both onto and one-to-one characteristics. So here is a good example. If you see like this below diagram, for f from x to y is injective because every single element 1, 2, 3 gets matched with some kind of distinct element of y, dbc. And here the function g, if we define it to be a function from y to the set z, is surjective because every single element of z, p, q, r gets mapped with some of the elements. But we cannot say g is one-to-one because c and a share some kind of same y value. We cannot say x to the y is surjective because the element a in set y is not matched with some kind of x value. So if you say there is a function h from the x to the z, you can say it's bijective because 1 gets matched with p, 2 gets matched with q, 3 gets matched with r. So it's bijective. So when you do the division over reals, as I told you, dividing by x is basically same as you just multiply it by 1 over x. So if you say 1 over x is equal to y, then you can just assume that y is the number such that x times y is equal to 1. Of course, there is an exception. You cannot do division over 0. Then such like y does not exist because you cannot define the sum integers, reals over 0, right? You follow the same logic in the modular, but it's kind of different. So try to focus on a little bit. So if we'd like to divide something by x mod m, as we did in the reals, we're going to find some kind of number y mod m such that xy is congruent to 1 over our modular system. So dividing by s modular m will be the same as multiplying by the y modular m, right? So subtraction, like we did addition and subtraction already. So you can think subtraction as also the inverse of addition, as we subtracting b modular m is just the same as adding minus b. So if we define the y to be the multiplicative inverse of x modular m, y is the value that makes x times y over mod m to be congruent to 1. So here's an example. If you have x is equal to 8 and m is equal to 15, the multiplicative inverse of 8 modular 15 is basically 2. because if you find the product 2 times 8 is equal to 6 and is congruent to 1 over mod 15. But the problem is we had an exception when you dealt with arithmetic, right? If you did a division over 0, no, it's impossible. So like those multiplicative inverse always exist. You should be aware of like 2 warnings. Modular is pretty different. There are like more cases than the general arithmetic because no multiplicative inverse might exist for a number which isn't 0. And also the product of the 2 non-zero integers might result in 0. So if you consider this 12 and 5, 12 is basically congruent to mod 10 and 5 is just 5. So you already know that these two numbers, integers, are 0. But if you multiply that, they become 16, which becomes the multiples of 10 and makes the whole modular equation to be congruent to 0. So how can you avoid this problem? This is kind of like a long proof. You don't need to remember it, but I just wanted to like actually help you guys to how to like proceed this kind of proof, because in terms of the modular and discrete mathematics, it's pretty important to structure the pretty concrete proof on your own. So let's say we have a theorem. So multiplicative inverse only exists if x and m are co-prime, which means their greatest common divisor they basically shares is 1. And then multiplicative inverse is also unique. So we're gonna like now like prove this one. So if you consider like this sequence 0 to the x, 2x, and to the n minus 1x, which are all distinct with respect to the mod n. So we are saying these are distinct because we already set up that the greatest common divisor between m and x is 1. So you already know that there are m values because the numbers in front of x is 0, 1, 2, n minus 1 inclusive. So we have like m distinct values here, which means for each x distinct values, which means 1 to 1, if we have an inverse, it must then be the case that ax is congruent to 1 mod m for exactly 1a. So there should be always a unique inverse for like each multiplicative inverse of x. So to prove this, what you're gonna do is you're gonna prove by contradiction. Suppose that there are two multiplicative inverse a and b, which are the same and distinct, then you can construct this equation to be the difference, right? A minus b times x should be congruent to 0 because it should be multiples or integer multiples over like m. However, you already know that x and m are relatively prime because it's what we define. The greatest common divisor to be 1 means it should be always relatively prime. So here, out of two terms, x cannot share any factors with m, which means to have a greatest common integer, common divisor, then like this implies that the difference must be an also integer multiple of m. But you already know that a minus b ranges from between 1 and m minus 1. It cannot be 0 because a is not same with b, so a minus b should be always some kind of non-zero number. So that is why if we have the co-prime numbers for x and m, there is always a unique inverse exist. So let's think about this case. Division in modular arithmetic, then you should always use inverse operations. So let's try this example. 8x is congruent to 9 mod 15. And if the question asks you find x, what are you gonna do? The hint is the unique multiplicative inverse exists because 8 and 15 are co-prime. So there should be an inverse exists with a certain value. So try some of the first numbers, 0, 1, 2, and find the actual value that makes 8 times something to be congruent to 9 over mod 15. If you, oh yeah, okay, someone is already posting the answers, so that's great. All right, great. I will just like wait about like the other like 30 seconds to hear for others' answers. Okay, I'm getting a lot. Thanks, guys, for the active participation. 3, 1, 3, 3, 1. Okay, seems like I got about 10 answers. And it seems like most of you guys told me the answer for the x is equal to 3. Yeah, that's perfect, guys. So the process is this. So if you were to solve like this equation, 8x is equal to 9 over the rationals, you just do multiplication both sides by 1 over 8, right? And you do the sorry, it's 9 over 8. And you do the same thing with the multiplicative inverse in the mod system. So we already talked about the previous example that the multiplicative inverse of 8 over mod 15 is 2, because 2 times 8 is congruent to 1. So if you multiply both sides by 2, you can just get x is congruent to 18, since 18 is 9 times 2, and 18 is congruent to 3 over mod 15. So this solution x congruent to 3 is basically unique with respect to the module 15. So always be careful that it might be not always possible to perform division in modular arithmetic if a multiplicative inverse doesn't exist. It is similar to the division over 0 in general arithmetic. So in this case, you just kind of found the first one. You just kind of tried the first sum of the factors from 0 to 2, and you just easily found that, well, 2 is an inverse for 8 over mod 15. But if you have a pretty big number, such as like 1,000 like bits, then it will be a little bit harder, right? Because you try to every single number from 0, 1 to that number minus 1 to actually find the one unique inverse. So the greatest mathematician called Euclid just made one algorithm. So usually if you have ever had Euclid's GCD algorithm, you might have seen some kind of recursive approach. But for the understanding, I will just introduce it in some of the more iterative approach, because I think it's way easier to understand it in the iteration rather than the recursion. So there's one important identity you should know. For the greatest common divisor of A, B, it can be always expressed to the linear combination of AX plus BY. And we already know that to have an inverse exist over mod, this GCD should be equal to 1, because X and M should be always coprime. Then, if you take the mod M over like this equation, Bm is an integer multiple of mod M. So you can just say AX is congruent to 1 over mod M. So here, A times X is 1 over mod M. So A is the multiplicative inverse of X. This is how you basically found the inverse by using the greatest common divisor. But how to find the A? There's another theorem that is pretty interesting, which is called Euclid's theorem of GCD. So GCD x comma y should be equal to GCD y comma x over mod y. So to prove this theorem, you can think of like this number d, which is a common divisor of x and y, only if d is a common divisor of y and x over mod y, right? Then you can think that, well, you can write out the x always to be the multiples of y plus some kind of remainders. And you can also say R is equal to X mod Y by the definition of the modular, right? If D divides the X and both Y as a factor, then it should also divide X and the multiples of Y, which implies that this also divides the difference R equals K minus QY, or is X minus QY, sorry. So X is also a multiple of K, QY is also a multiple of D, so you do KD. So where the K is an integer, this can be expressed as a D multiples of D. So converse also holds, so we just proved that, wow, we can use the GCD x comma y equal to this GCD. So there's an example on the left side. GCD 16 comma 10 is equal to 10 comma 6. 6 is just 16 mod 10. Here 4 is 10 mod 6. 2 is 6 mod 4, and the 0 is 4 mod 2. Well, you can divide like 0 with like any numbers, which results in 0. So in this case, the greatest common divisor is just 2. So this is just the basic example. So the basic process is use the above theorem to get the GCD until you get some kind of equation for 1, and then you're going to take the mod M. So let's try some example. How to find the inverse of the 61? Oh, sorry. Oh, yeah. How to find the inverse of 61 over the modular 97? So first of all, what you do is you write the linear combination of 97 and 61. And it's pretty simple. 97 is just 1 times 97 plus 0 times 61. And 61 is equal to 0 times 97 plus 1 times 61. And this is just the equation for the greatest common divisor of 97, 61. And now you will do the similar approach as the picture of the left suggests. You are going to go down until you get the expression of 1. So first of all, you do the 97 over mod 61. And it's basically same as 97 minus 61 times 1, right? So you get this 1 and minus this 1. So it is 97 minus 61. And this is the expression of greatest common divisor of 61, 36. You do the same thing, 61 over mod 6. And it's 67 minus 36. So you were going to get 0 minus 1 here. and 1 minus 1, which is 2. If you do the same thing, 36 minus 25 is 2 times 97 minus 3 times 61, and blah, blah, blah. So you try to like iteratively approach until you get some kind of expression for 1. So if you see the last one, if you take the 3 over mod 2, we know that is a congruent to 1, which is 3 minus 2. So you get is 3 minus 2 is 3 minus 2 times 1, right? So you get is you do 17, and this minus 5 congruent to like 22, and you get 8 minus 27, which gives us 35. Or actually, there should be like minus in front of 22, my mistake. So now you have an equation for the number 1. Then what you need to do is we were trying to find the inverse of 61 over mod 97. So you will take the mod 97 on the both sides. So with this equation, we'd like to find the inverse. So if you take the mod 97, this first term gets erased because it's just the inner multiple of 97. So what you have is 35 times 61 is congruent to 1 over mod 97. Since we wanted to find the inverse of 61, so we can just say inverse of the 61 is congruent to 35. And you can check the calculation by doing 61 times 35 is 2135, and it's basically some multiple and plus 1. So our calculation was correct. So we just talked about the basic arithmetic, how to do the addition, subtraction, multiplication, and division. There is also an important theorem called Chinese remainder theorem, but due to the time constraint, I would not cover it. If you'd like to take a look on the CRT, please take a look at the Mark's lecture tomorrow. He will bring on more examples of the modular arithmetic and Chinese remainder theorem. So we're going to talk about how can modular arithmetic be pretty strong in the system of the cryptography. So in the cryptography, it's a pretty ancient subject. That really blossomed into its modern form at the same time as the other great revolutions in the general fields of information science and engineering, so CS actually. So this is the basic setting for the cryptography. There are a cast of 3 characters, Alice and Bob, who are doing the communication confidentially over some kind of insecure link. And there is also a Eva, who is an eavesdropper who is listening in and trying to discover what they are talking about. So she's trying like cheating on it. So let's assume that Alice wants to transmit a message called X to the Bob in a secure way. Then she will gonna apply her encryption function E so that it could be securely encrypted and send it over the link so that someone cannot like actually decrypt that message without having certain decrypt function that fits to EX. Then Bob, upon receipt of encrypted message, will apply his decryption function called D over it. So he would be able to recover the original message DEX is equal to the original message X. So for the past centuries, the cryptography was mostly based on what are now called a private keys. So by saying private keys is Alice and Bob just meet beforehand and choose a secret code generation scheme together, with which they will gonna encrypt all future correspondence between like this scheme they created. This is pretty useful because there is a chance that it might get hold of EX, but they just like define the EX before they actually transmit the message. But there is still a loophole. So what happens is if they transmit too many messages and they kind of collected a lot of data, it might be a little bit difficult, but she can just do the pattern matching to actually successfully find the EX and try to find how they actually encrypted and find the actual general code scheme here. So now the computer scientists just developed the one protocol called public key. So now it's kind of like awkward because now Alice is just sending Bob a message without ever having met him before. Because we're gonna just say the encryption key and encryption function is public, even if who's like doing eardropping is aware of what it is, what is that function. And Bob himself has his secret/private key that can actually decrypt the message that Alice sent. So it is more like Bob is able to implement a digital lock that only he can actually resolve. So the most representative scheme using the public key protocols is called RSA. So each person has a public key known to everybody and a private key only known to him or herself. Then if someone wants to send a message to like Bob, for example, then the sender should encode it using Bob's public key, the recipient's one, and Bob, upon like receiving the encrypted message, we're gonna decrypt it using his private key. So they use a modular arithmetic for this amazing protocols that has been often used in over like 50 years since 1970s. So the procedure is pretty long, but we're gonna talk about it with a similar, more simpler example. So usually what you do is you just pick the two numbers P and Q, which are pretty large prime, which is like 500, 120, 512 bits, 1024 bits, 2048 bits, something like that. And you just define N as a product of PQ. And you are gonna think of every single message that's sent to Bob on the modular field. So you're gonna think of the message that has been converted into the binary codes, which is the language that computer actually uses, as the numbers respect to the modular N. Then we're gonna pick the E. So here E is used for the encryption. So we'll make the E be any number that is relatively prime to P minus 1 times Q minus 1. Is not the P times Q. Typically we'll just choose E to be a small value. So why did we like choose E to be a number that is relatively prime? It's because we need to use the multiplicative inverse upon the RSA scheme. Okay, so there's a question. Can someone come up with a decryption key based on the public encryption key? If so, doesn't that defeat the purpose of having the private decryption key? Yeah, that's definitely a great question. And most people are having a very similar question where they just first encounter the RSA scheme. But we're gonna talk about like why RSA is pretty strong at the end. So yeah, please stay tuned. So we're gonna set the public key as a pair of numbers, N equals PQ and the E we choose. And then we want to set private key to be the number. So this D is the multiplicative inverse of E mod P minus 1, Q minus 1. And it's certain that like this inverse exists because E and this two is co-prime. So we are sure that there should exist a unique inverse called D. Now you're going to define the encryption and decryption. So what you do is you will define the encryption as x to the power of E mod N. And the decryption is y to the d mod n. So if you get the d and ex, which was the original goal of the RSA scheme, if you put the d xe over here, it becomes x to the power e times d. And here, e times d is congruent over 1 over mod n. So basically, you can just deal with this as an original message. So let's look at the example. If someone just decided to pick P and Q becomes 5 and 11, you define N becomes a product 55. And choose E equals 3, which is relatively prime. So the public key is 55 and 3, which is N and E each. And private key is D, inverse of 3 over mod 40, which is 27. So if the Bob sends a message, Bob gets the message, which is called X equals 13. The actual encrypted message he would get is 13 power of 3, which is 52 over mod 55. And after Bob gets message, he'll apply the decryption. So it's a 52 power of 27, and it's basically congruent to 13 mod 55. But those RSA scheme always work. We already talked about the inverse, so we know that inverse exists, but there's a question. Can RSA always can correctly recover the message that has been originally sent before it gets encrypted? Well, to prove that, we need to learn just one simple theorem. It's called Fermat's little theorem, but don't worry, it's not as hard as like his last theorem. So like FFT basically states that for any prime P and any A that is 1 to P minus 1 inclusive, if you take the A to the P minus 1, it is always congruent to 1 mod P. So if you think of the proof, we're going to think about two different sets, 1 to P minus 1 inclusive, and some kind of sequence that is A, 2A, 3A to the P minus 1A over mod P. You know that the GCD of like P comma A, the greatest common divisor, is basically 1 because P is prime and A is always more than P. So A cannot be a multiple of P. So you can define that these numbers of both sets are all distinct. They have the same cardinality. So we will now take the product of all numbers in the original set, which is 1 times 2 times P minus 1, which you can express it using factorial, P minus 1 factorial. Let's compare it with the products of S prime. So it's A times 2A times P minus 1A, which is congruent to A to the P minus 1 times P minus 1 factorial. So we already know that because both sets have the same cardinality, and those sets of numbers are exactly same over the mod p, then you can say these two equations of products should be always equal. So what you do is you set up this equivalence. P minus 1 factorial is O. It should be A to the P minus 1 and P minus 1 factorial. If you multiply both sides by inverse of P minus 1 factorial to get P minus 1 equivalent 1, well, it's done, right? But here it is pretty important thing is P minus 1 factorial, we can certainly say it has an inverse mod P. Because inverse is basically the product of every single inverse for each of 1, 2, P minus 1. Because P is prime, so that every non-zero integer has an inverse mod P. So let's take a quick example. If you try to find 220 plus 330 plus 440 plus 550 plus 660 using FLT over mod 7, how can you do it? Does anybody have any ideas? The hint is this prime P and any FLT always holds for any prime P. Here the P is basically 7 and the any number A. A is basically 2, 3, 4, 5, 6 each. Yeah, if anybody has ideas, just feel free to send me a message or just feel free to speak up. I'll just wait for around 1 to 2 minutes. Oh, all right, cool. Someone just mentioned that, well, 2 to the power of 6 is congruent to 1 over mod 7 due to alpha t. Yeah, and it is correct. Yeah, thanks for sharing that. So P minus 1 here is basically 6. So you can think of each 2 to the 6 and 3 to the 6, 4 to the 6, 5 to the 6, and 6 to the 6 are all congruent to 1 over mod 7. So you can simplify this equation by modifying it to be 2 to the 2 plus 3 to the 0, 4 to the 4, 5 to the 2, and 6 to the 0 by subtracting the largest integer multiple of 6 from the exponents. And it gives us 4 plus 1 plus 20 plus 25 plus 1. So if you rearrange it to the equation over mod 7, you will get 14, which is the multiple of 7, so it's congruent to 0. So what does FLT actually implies in terms of the correctness of RSA? This is pretty important because when we deal with the RSA, we need to always make sure that for every possible message, if we put the encrypted message inside of decrypt function, we always get the original. And ours can always decode the message successfully. So we already defined the encryption to be x to the power of e and the decryption to be y to the power of d. So to prove this dex, you just prove that x to the ed is congruent to x for every single possible message, right? Oh, we already know that ed is congruent to 1, which is d is a multiplicative inverse of e, so therefore it should be always 1. So we're going to use the FLT. So we're going to like rearrange our equation a little bit. So x to the ed is congruent to x can be modified by using the subtraction properties. X to the ed minus x is congruent to x minus x, which is 0 over mod n. So by the definition of the congruences, we already know that ed is equal to 1 over the p minus 1 and q minus 1 mod. So you can express ed as a sum of 1 and some kind of integer multiples of k times p minus 1, q minus 1. So now you can think of like this equation like that. You change ed to be 1 plus k p minus 1, q minus 1, and you're gonna like try to factorize this with x. Now, you need to consider the two cases. The easier case is if x is a multiple of p, then, well, the whole expression is clearly divisible by d. So the modular of itself is just congruent to 0. So it's true. But the case where x is not a multiple of p, in this case, FLT is pretty useful. So if x is not a multiple of p, you can use the FLT to deduce that x to the p minus 1 is congruent to 1 over mod p. So that you can think of like this ax, k, p minus 1, q minus 1, minus 1. You can just factorize this to be x to the p minus 1, which is 1 to the power of something, which is always 1. So you get the congruences. You can prove the same thing over a mod q so that you can prove like this term is divisible by q. So since you know that this term is divisible by both p and q, and you know that p and q are primes, which implies the product of these two primes should be also divisible by their product. So this means the expression is always equal / congruent to the 0 mod n. So now let's talk about the question that number 154 as, then why we can like use RSA in a secure way? Isn't it like really easy to actually break it down? Because if we know the prime factors, we can just factorize m and actually create the decrease function. But the point is, we only talked about the small prime numbers such as 5 and 7 when we do the RSA example. But when you use RSA in the computer, when you deal with the VPN, internet or message, iMessage or SNS and banking account, all of those places, when you use the RSA, they always use a sufficiently large prime. Well, then we need to think about, well, if we use the sufficiently large prime, wouldn't it be also hard to calculate those kind of schemes for both Alice and Bob, who would actually communicate from the channel? But the point is, Bob has to find the prime numbers P and Q, which has just sufficiently many bits. And they just need to compute the exponential, right? And we already know that it's pretty easy to find the exponential expression. So the naive approach to find the expression for the exponentiation is find the x mod n, x to the t mod n, x to the 3 mod n, x to the 4 mod n, so forth. But there is also a very efficient technique called repeated squaring. So if you know x, you can find x to the 2 by doing x times x. And then you don't need to find x to the 3, because what you're going to do is you will do x to the 2 times x to the 2 so that you can find the x to the 4 over mod n. It holds for like every same exponents, which is the powers of 2, like x to the 8, x to the 6. So if you do like this repeated squaring, this multiplication takes only n loop time, which means it takes like n multiplication maximum that we need to do. So Alice and Bob can perform much simpler and way more efficiently. But the point is, we are dealing with a sufficiently large prime. So if you'd like to create the decryption function, you need to know what is the actual n can be factorized. Because in the public key, the only thing you can know is the value of n and e for some third person. So to find the p and q, those values, what you need to do is you need to find how n can be factorized into exactly 2 primes. And it takes way larger time to actually figure out those primes, because there are like infinitely many prime numbers, and you should always check from the very first prime 2, 3, 5, 7, and 11, like go for it. So it's like pretty impossible to actually find the decretion function, because it will take like way larger time than you expected to actually figure out how can n actually factorize. If you are interested in why like this, like prime factorization takes a lot of time, you need to understand a bit of like algorithm classes of the computer science majors. So yeah, try to look for it. But yeah, today my objective was to help you guys get familiar with the modular arithmetic, which is pretty important and useful if you like to explore the field of the computer science and math. And hope you guys have understood how our everyday cryptography, how when we always like send our like message with like we exchange our message with our friends, when you go to like your banking account and those kind of like things you do on the internet and computer can be protected through like these RSA algorithms, which uses modular arithmetic heavily. Yeah, this is the end of my lecture, and thanks for your listening.